Here at MPIA we have large technical departments with some 40 people working in them. We develop and build instruments for different observatories and telescopes, mainly working at infrared wavelengths, which are wavelengths that are slightly longer than the visible light. We have 5 different technical departments. One is construction, where we design different mechanical parts for instruments. Then there's the fine mechanics, where they actually in the workshop build these parts. Then we have electronics department, which designs and manufactures different electronics for the instruments. Then we have the software department, where they write the control software for these instruments and subsystems. And finally we have the so-called instrumentation department, where we have experts on many different fields working to build these instruments. We have experts in optics, on detector systems, on cryogenics, also in systems engineering and project management. And all these people work together to build these fantastic new instruments for different telescopes. Here in-house we have different facilities for building these instruments. We have clean rooms for dedicated instrument testing and integration, and we have large integration halls for bigger parts that we need to integrate. We have electronics workshop for building the electronics, and we also have the mechanics workshop.
Here in our workshop, in the precision mechanics workshop of the Max Planck Institute for Astronomy, we are building and manufacturing components for ground-based observatories and space-based satellites. These are things that you cannot purchase from the shelf, and that's why we need our own workshop. In my time at this institute, I've seen of the order, say, 15 or so instrumentation projects, some very little, others very big, and I'll give you a few examples. We've been involved in instrumentation mostly for ground-based telescopes. One is the Large Binocular Telescope, which is on a mountain in Arizona, United States. There we installed the biggest instrument we've ever built. It's called Link Nirvana, but we were also involved in the Lucy spectrographs. These are 2 spectrographs there that were integrated here in-house. Then we made instruments, or we participated in making instruments for the European Southern Observatory, which is our main customer still, and the list is long for them. For example, we were involved in gravity, which helped to get a Nobel Prize.
And this instrument is very interesting because, the research that it focuses on is studying the stars that go around the supermassive black hole in the center of our galaxy. And actually this research, partly powered by gravity, got the Physics Nobel Prize in 2020.
We have instrumentation all over the world, and then we also have the space department that was involved in a few space missions. Recently the Herschel mission, currently the recently launched James Webb Space Telescope, where we delivered some of the mechanisms. And also for the next, one of the next space telescopes, the Roman space telescopes, this workshop especially was very good in providing several of the mechanisms that are required there. Here you see our latest addition to the machine shop, a 5-axis milling machine that we recently purchased in order to be able to manufacture larger pieces that are needed for projects for the next generation telescope, the extremely large telescope currently built by ESO, the European Southern Observatory in Chile. We needed this larger machine because the several machines that we already have were not big enough for the manufacture of certain components that we need to prepare for these instrumentation.
Currently we are very busy building instruments for the next big European project, which is the extremely large telescope that is being built in the northern Chile. This is a project that takes a long time. This has been already been planned and built for a decade, and we are still not there, so it will take some 4 or 5 years more. One of the instruments we are building for ELT is METIS.
METIS is one of the first generation instruments for the extremely large telescope in Chile. So METIS stands for Mid-Infrared ELT Imager and Spectrograph. METIS is built by a consortium of international partners with the MPIA Institute in Leiden, Nova. And here I have a small-scaled model for METIS. The heart of METIS is a cryostat. In reality, this is 3 meters high and 3 meters in diameter, and inside METIS there are 2 scientific instruments, a camera called imager and a spectrograph called LM-band spectrograph, and also some wavefront sensor for the adaptive optics. And on top of this cryostat, which is used to cool everything down to 70 K, we have a warm calibration unit. The complete cryostat and calibration unit are held by a warm support structure, and underneath you see electronic cabinets. We just passed the final design review. That means we are now in the manufacturing phase, and it will take us a couple of years until all of this will come together and go to the ELT. MPIA is the second largest partner in the METIS consortium. We are responsible for the imager, which is a camera for the LM and N band, capable of doing high contrast imaging as well as spectroscopy, and the adaptive optics subsystem. So the adaptive optics subsystem is essential to cancel out the effects of the atmosphere, and we have inside the cryostat a wavefront sensor which is sensing the atmosphere and the flickering of the starlights, and then we have a real-time computer and software outside, and this is calculating the correction signals which are then applied to the system to have a brand new and great star signal without any atmospheric effects.
In addition to METIS, we are also part of the team building MICADO, which will produce sharper images than the James Webb Space Telescope.
So, this is the Montagehalle. It is the biggest integration hall we have here at MPIA, and we will use it in the next few months to start the integration of our MICADO subsystem.
So, here we will integrate the subsystems for MICADO, which come from MPIA. These are the relay optics and the calibration unit. Both of them will be assembled here and tested for the next couple of years, and afterwards they move to Garching and will be integrated with the rest of the MICADO instrument.
So, what we see here is one of the prototypes we use for the relay optics subsystem. This is a mirror which is used in the end on the relay optics to align and fold the beam from the ELT into the MICADO instrument. So the prototypes were used in the last years not only for pre-testing stuff, but also to find about deficiencies, design flaws, interface problems. So this was very helpful in the past. And it marks also now the start of the nominal hardware, where we also expect major challenges in finding out other surprises of our hardware. So the interesting thing about these prototypes is that they mark a kind of a transition from a very long paper phase, where we've done analysis work and documentation, to the real hardware and software phase, which is just about to start now. This will bring all the hardware together. We will have a very long test campaign here at MPIA, and in about 5 years from now, everything will then be shipped to the telescope.
As an astronomer, it's really great to work here at the technical departments, being part of the team that is building the state-of-the-art future instrumentation that will enable all the exciting scientific discoveries in the future.